Okay, this is the review for the final midterm, or the final. As in the previous weeks, it will be 8 till 8:30, Monday, Wednesday and Friday. It'll be in week 15. If you have problems in submitting, as before, then just send a photograph of your script or whatever to me. That's something that's time-stamped as soon as you can, and then we'll deal with it at the other end. So the material for this test is the last 3 weeks' work, I suppose. Pipes and pipe networks, mainly pipe networks. External flows, which was week 12, and then open channel flows, which was week 13. And join us for each of the 3 days, all of them, on Monday, Wednesday and Friday, not just for one of them. The first one deals with pipe networks and the use of Bernoulli's equation written in terms of the energy equation. The second one is on external flows, and the third one is on open channel flows. So I'll just go through the material that's relevant to the individual topics which are appearing on the class. The first part is the energy equation. So we know that we can write the energy equation. We have to write it between upstream and downstream. And so we have to be careful to write it upstream to downstream with the magnitude of a pump head existing on the upstream side and the losses either as pipe losses or as losses in fittings and bends as these head loss parameters, H sub L. And so we have to be careful to write it always from the upstream location to the downstream location. The pump head we can always define in terms of power and the mass flow rate. So W dot is power, M dot is mass flow rate times gravity. And if we write the mass flow rate out in terms of a density times a volumetric flow rate, we can write it in this form. The head losses are written in terms of velocities. These are velocities through the fitting or through the pipe. They have to be, together with the length of the pipe, the diameter, and either a loss coefficient or a friction factor. Both the friction factor and the loss coefficients are non-dimensional parameters. They have no dimensions, and they're just a scalar to be able to operate on this velocity head term in each case. If we use the energy equation for pipe flow, we use it also for open channel flows, and we know that the factors that modulate the frictional losses in these systems. For pipe flow, it is the friction factor. For external flows, it's either the coefficient of drag or the coefficient of lift. And for open channel flows, it's defined in terms of the Manning coefficient. So those are all parameters that give us loss within the system. And the behaviors are all the same as we've talked about many times in class. For pipe flow, if we're trying to work out the magnitudes of the friction factors, it matters whether the flow is either laminar or turbulent. The transition between those regimes occurs at something like a Reynolds number of 2000. Reynolds number is velocity, density, hydraulic diameter, and viscosity. And the behaviors are quite different in that in the laminar regime, the friction factor is a function of Reynolds number. Typically for a circular pipe, this value here is 64, as you know. But in the turbulent regime, the friction factor is not a function of Reynolds number. The curves are flat, but it is additionally a function of the relative roughness of the pipe, given as the absolute roughness divided by the hydraulic diameter. And that's what's represented here. So for laminar flow, the friction factor is a function of Reynolds number, but not a function of the roughness. And for turbulent flow, the friction factor is not a function of Reynolds number, hence these curves are flat, and is a function of the relative roughness. There are 3 classes of problem solutions that we've talked about in class. The simplest one is where you know what either the flow rate is or the velocity, in which case immediately you can calculate the value of the head losses and you have a solution in one step. In the cases where you are not given the velocities and you have to solve for the velocities, then you typically have to choose a Reynolds number, calculate from that Reynolds number a value of the friction factor, use that friction factor to calculate a flow velocity, and then use that to recalculate a Reynolds number, and then go back in and make sure that you iterate onto a single location where you're no longer changing anymore. Typically, it's a bit easier to solve these in exam questions because you can solve it in one step. But also there are other systems where you can solve it. So this is where that sequence path is. You have to select a velocity. From a velocity you can calculate a Reynolds number. From a Reynolds number you can calculate a friction factor. And from a friction factor you can recalculate a velocity. You can check that Reynolds number is similar to the one you used before. If it's not, then you go back through the sequence and then you come out at the other end. We've talked about pipe networks, so we have more than one pipe flowing. We've talked about the cases of when you have parallel or series flow. In parallel flow, then by definition, the head drop between the upstream and the down reservoir is the same for all pipes, and so the head losses for all of the individual components between upstream and downstream are the same, but the total flow from the upstream to downstream is the sum of the flow rates in pipe 1 and pipe 2, and if you have other pipes in the system also. If you have a pipe network which is in series, then you know that the volumetric flow through pipe 1 is equal to the volumetric flow through pipe 2. So the flow rates are the same in all pipe sections, but the head losses are cumulative as you go from upstream to downstream. So that defines the way in which you wish to solve the problem. If you have a branching network, then you know for sure that the pressure in both of these legs, leg 1, leg 2 and leg 3 is the same, because if it comes into a tank at this downstream side, the pressures at these 2 points are the same, the pressure has to be the same here, so the head losses have to be the same over these lengths because they change the same amount as they go from point 1 to 2 and point 1 to 3, hence the head losses on the second part of the circuit are the same. If we look at external flows, then we've made the point that the friction factors, if you like, for external flows look exactly the same as they do for pipe flows. I suppose the difference in pipe flows is that we're interested in pipe flows in the effect of friction on the flow rate for flow through the pipe, and we'd like to calculate what that modified flow rate is. In external flows, we have a flow rate, and that flow rate doesn't change very much, but we're interested in what kind of force that flow rate exerts on the structure it's flowing past. But the friction factor curves look the same. They have this laminar portion and a turbulent portion. The laminar portion is a function of Reynolds number, and depending on the shape of the structure, this has a number attached to it. And in the turbulent regime, it's a bit more complicated, is that they're not flat for all of them, but they sometimes have some undulations. But essentially, for a given structure, a sphere or a cylinder, these are constant with Reynolds number, shown by the fact that these curves are horizontal. The friction factor now, instead of being a friction factor, is really an Euler number, and we define it as a coefficient of drag or a coefficient of lift. The only difference is that this is acting in the direction of flow, and this is acting, this is directing horizontally, and this is acting upwards in terms of the direction. And we know that if we can calculate what this magnitude of the coefficient of drag is, and we know the velocity at which we're flowing, and we know the cross-sectional area, maybe the planiform area of the structure and the density of the fluid, then we can calculate this final term here, which is the frictional component. So we can rearrange the drag coefficient into this. If it was a lift coefficient, then it would just be a coefficient of lift, and these same terms added onto it. And if, for instance, we know what the coefficient of lift is, the density of the fluid, the velocity, and the area of our system, then we can calculate the magnitude of lift applied to the component. If we know what the lift force is, then we can use Newton's second law. We could use it to calculate out of balance forces and accelerations, or if the acceleration is zero, in other words, it's moving at a constant velocity, then the sum of forces acting on a structure balance. And so, for instance, the lift force has to be equivalent to the mass times gravity of the structure. And so we can do balance behaviors so that we know that the fluid flowing up past here is exactly balanced by providing a lift which is equal to the gravitational force applied by the weight of the structure. Again, if we're dealing with external flows, the coefficient of drag or coefficient of lift is a function of the Reynolds number for laminar flow. So for anything less than a Reynolds number of 2000, that's the case. And if we're in the turbulent regime, then the coefficient of drag is no longer a function of Reynolds number, hence being flat, but is a function of, is a constant magnitude irrespective of Reynolds number, and it allows us to calculate the velocity of flow to give a given force acting on the structure. And so fundamentally, the way in which we calculate the velocities or the velocity squared in each of these is controlled by the regime we're in. If we're in the turbulent regime, then we end up with a component here which is a function of v squared for a constant value of this. If we're in the laminar regime, then the coefficient of drag is a function of the Reynolds number. The Reynolds number goes into this term here, and one of these velocities gets cancelled out, and we end up solving an equation which is just a function of velocity, not velocity squared. And so there are different ways in which we solve for flows, if they're turbulent or laminar, depending on whether we solve an equation which is in this form or in this form. So the third and final topic is open channel flows. We've talked about open channel flows and gradually and rapidly varying flows. Only open channel flows and gently varying flows are used on this particular test. And so these are the expressions that you would need to understand. We know that the volumetric flow rate is equal to the average flow velocity within the channel multiplied by the cross-sectional area. The cross-sectional area would be the width times the height of the flow. We know that we can use Manning's equation to get an average velocity, which is a function for SI units. This term is equal to 1. Manning's coefficient is a dimensionless number, maybe of the order of 100, something of that, and two other parameters, the hydraulic radius and the slope, dimensionless slope of the channel bed. The slope of the channel bed is given by the drop in the bed over a given length. So this would be the length here, given by the drop that occurs. And the hydraulic radius is just the cross-sectional area of this flow divided by the perimeter. The perimeter is equal to this green curve here. So in this particular case, for a channel of width W and height Y, the area is going to be the product of the depth times the width, and the perimeter is going to be the portion along the base, which is W, plus 2 times the vertical depth on the sides. And so it's the ratio of these two. Also, if we want to use a Reynolds number for this, we rarely do this because we know for most cases of open channel flows, the flow is turbulent, so it's above the threshold. but the Reynolds number, if we need it, is defined in terms of the hydraulic radius, which again is just the area of the perimeter. If we need to calculate the average velocity, and we know what the depth and the width of the channels are, then we can calculate the hydraulic radius. We need to know the slope of the bed down gradient as it travels, and we can get the average velocity from this. If we need to know what the volumetric flow rate in the channel is for the total flow, then we multiply the velocity multiplied by the total cross-sectional area of the channel to get the volumetric flow rate. And that's about it, I think. So these should be all the expressions that you need for the final, and good luck.